Hello everyone, welcome to Compass Lecture Series. Our today's speaker is Dr. Behnam Esmayli, visiting assistant professor at University of Cincinnati, USA. And today he will be talking about Sobolev functions on weighted Rn. Over to you, Behnam. Thank you.
Thank you. Thank you everyone for being here. Thanks to the organizers, especially Abhishek, for the kind invitation. So yes, he actually gave the correct title. I was going to mention that by weighted Sobolev function, we actually mean Sobolev functions on a weighted Rn. It's not that we weight the functions, we weight Rn, we put a new measure on it, and then talk about Sobolev functions in this new setting. Please feel free to interrupt at any moment for any questions. After all, this is just an expository talk. So my talk starts by talking about the Sobolev functions in the very standard setting of Rn. Then I talk about weighted Sobolev functions and discuss a couple of features, properties of those functions. So in the standard Euclidean setting, the textbook way one is introduced to Sobolev space in a 300, 400, 600 book is they start by talking about weak derivatives. And then, oops, apparently I'm not as ready as I thought I was. So you talk about weak derivatives, and then you try to prove that those weak derivatives are actually strong enough so that even though your derivative is in a generalized sense, it still has some nice features similar to smooth functions that makes us able to still do calculus. So the problem with that is that it's just out of blue. So we have to admit we never do, because when we're reading a book, we assume everything is just tested. And of course, that is the only way we can talk about Sobolev functions. But if we really think about it, the definition of weak differentiability is quite unnatural. It's unmotivated. So the first question shouldn't be what are Sobolev functions, but rather why Sobolev functions. So why do we even consider talking about Sobolev functions? The short answer obviously is to solve PDEs. And here is a very simple example. So what happens is we want to talk about solutions to this. What's happening with this thing? Okay, I'll switch to this finally. The simplest is always the best. So we want to talk, say, about solutions of this problem on a nice domain. We can transform it to a minimization problem. Among functions with the same trace boundary value, the one that minimizes this energy will also solve this. So in order to find a function with this property, it's enough to find a function that minimizes this energy. But you know how to do minimum problems. We take a sequence that minimizes. So a minimum is a number, so there are a sequence of functions so that integral gradient ui to the power 2 converges to that infimum. And now if we are able to say that some subsequence of this converges to a C2 function, then we will have that this u function satisfies this equals 0. I'm asking it to be C2 because at this point I don't even know how to take second derivative of things that are not twice differentiable. So, but is there such a subsequence? Can we pass to the limit and end up with a C2 function? So here all we have is that these converge to an infimum, and that means we have these bounded. But let's even assume more and ask the same question, okay? Suppose that I have not just a bounded sequence, but a Cauchy sequence in this norm. That means I am asking that the LP norm of the functions form a Cauchy sequence, and at the same time, the LP norm of their gradients forms a Cauchy sequence. This is way, way more stronger than what was in the previous setting. Then again, I ask, is there a subsequence that converges to some smooth function? And the answer is no. And this is why we need Sobolev functions, because what could be stronger than this, and still we don't have a limit that we like. So that's why we have to talk about the animals, the objects that are in the limits of smooth functions under this. And those are going to be Sobolev functions. So technically, here's what happens. So if you are in the previous setting, if you have a Cauchy sequence in this norm, then individually these are a Cauchy sequence in LP, but LP is complete, so there is a limit U of these UI. So UI converge to this U in LP. That we know because LP is complete. And similarly, the gradients are in LP. You can talk about each coordinate separately, but I like to use this vector notation. So they also converge to a function. So this is again a function, and each component is in LP. So gradient UI also converge to gradient U. So we have solved the problem of, does it have a limit? Yes, it does. But what happened to these U and gradient U? They are not guaranteed to be smooth functions. So U is not guaranteed to be smooth functions. And although we love to call this vector gradient of U, this is really in this sense only. It's gradient of U in the sense that it's the limit of gradients of UIs where UIs approximate U itself. So for the time being, keep this as just quotation marked gradient. So what we managed to do is that if you have a Cauchy sequence in this so-called Sobolev norm, then the limits exist, but only as LP functions. And let's define H1P to be those functions in LP that you can realize as such. So smooth functions, at least compactly smooth functions, compactly supported, will be in this space because you can just take the constant sequence. So this set includes the compactly supported smooth functions. So it's not empty. 0 can be realized as such. But we also add, other than smooth functions, any function in LP that you can realize in this way. And in writing this U belong to LP, we're actually committing some mistake because we are assuming that this U alone is determining my function. Whereas we just didn't have information about the function, we had the information about convergence of its gradients as well. So in this notation, if we are really truthful, we have to say U and this V together are one object in H1P. And you will see that in the weighted case, this actually becomes important, but we are used to, from standard Sobolev theory, just to call U an H1P function. So warning, isn't this loss of information? It should be, but we will see that it turns out that it is not at the end of the day. So let's see, now that we have included some more objects other than smooth functions in our category, what can we salvage? What kind of properties are still true for these new LP functions? Should we be scared? Did we add too much? Why did we allow LP functions? Well, it turns out that one thing that survives is integration by parts. So you take an index k from 1 to n, which is dimension of our space, and a compactly supported function psi. Now, from the standard theory of calculus, this is multivariable calculus, everything smooth, we have this integration by parts formula. So everything here is meaningful in the classical sense. UI are smooth functions, and therefore these derivatives make sense, and psi, of course, is smooth, and they make sense. Now, we had U, a function in H1P, by definition, you had a sequence of UI that converged to U in LP, and the gradients of them converge to another LP function, which I still call VK. If you apply a Hölder's inequality, you can see that because UI converges in LP and partials converge in LP, if you take limit, this side will converge to that. Basically, you can just drop the index I. So as I goes to infinity, this side will converge to this side. And similarly, because you have LP convergence here, this side converges to that, but you had equality at every step, so this remains true. So you have this true for every compactly supported psi, and K is arbitrary also. But notice that your U and VK are no longer C1. So you still have the equality for your generalized LP functions. So this equality still holds even though U and VK are not continuous, for example. So the simple conclusion is just saying that H1P functions are weakly differentiable. This is exactly definition of weak differentiability, which I recall in a second. So what is weak differentiability, which would be the starting point of any book on Sobolev spaces? You say that a locally integrable function U has partial K of U, which is now in just weak sense equal to VK. You will say that VK is a partial of U if this holds for every compactly supported function. So we call VK the partial derivative of U. So this is page 1 of every Sobolev book. And as I said, I'm not a fan of it now because when I was reading it for the first time, you're reading this majestic theory of Sobolev spaces, and you open a book, every book you open, it starts with this. And you say, okay, well, someone woke up in the morning and said, I'm going to define weak derivatives, and this is my definition. And I think it's kind of very unintuitive. So the story that I told you is you start with C infinity function, you don't look for trouble, but then you look at very reasonable scenarios where you have sequences of smooth functions and you see that their limit is not smooth. So, but you do need limits, right? If you do any analysis, it's all limits. And to have the limits, you have to bring in some LP functions. It turns out these LP functions at least satisfy this thing. And from this definition, you can prove that these VKs are almost everywhere uniquely determined. So if you have another function satisfying this property, it is almost everywhere equal to the previous one. So these vectors are uniquely determined by your function U. That's why we can call it gradient U. So they are, because this notation makes sense because U determines these vectors. And finally, we define the W1P space to be those LP functions that have weak derivatives which are also in LP. Let's compare it to H1P. This was those U in LP that arise as limits of C infinity smooth functions. And I want to mention an important point here. So if you look at definition of weak derivative, I didn't say LP. I said L1, and I even said locally L1. First of all, why do we need this anyway? Because this is the weakest assumption so that you can make sense of these integrals. So for this integral to be meaningful, you want it to be L1. And because psi is compactly supported, it's enough to be locally L1. So to even write this equality, you need L1. And so to define the weak differentiability, you only need L1 local. But to be in W1P, you want more integrability. So you don't want just L1, you need LP. So if you wanted to give a kind of shortcut, you could just say we say some function in LP is in W1P if this happens with some VK, which is also in LP. But the point I want to make is that W1P space has two kind of separate components. One of them is a weak differentiability, which initially has nothing to do with the integrability part. And the second part is that it is in LP. So you check first that the function is weakly differentiable, and you check what is the highest power with which it is integrable. And this will become important later, which is why I'm mentioning. So the best news of all is that this H equals W. So in the previous case where I said that integration by parts is still true for these LP functions here, we basically just proved that these are subset of that. But also the converse holds. So how do you prove the converse? You start with a weakly differentiable function, which is also LP integrable. You want to show that it is an H1P. By definition, you need to find smooth functions that approximate it. And this is maybe page 2 of those Sobolev books, because the moment they define this W1P, it's basically admitting that this is so strange. And then they try to say that, well, wait, before you return the book, actually they are limits of smooth functions, so they are not really crazy creatures. So two ways of doing Sobolev spaces. You start by a very unintuitive, scary definition, and then you try to say that calm down, everything is good, these functions aren't as bad as you may think. The other one is you start with a smooth function and gradually end up in the world of Sobolev spaces, and your victims never know what happened to them. So no loss of information in the notation in H1P. Remember, in H1P, I said that you have these UI converging to U, gradient UI converging to gradient U. And then we said U is in H1P. And we said that, well, what happened then to this whole thing? Because now these are equal, this is a really corollary of that. Because these are equal, this vector V's are uniquely determined. So these were V's. These vectors, we just showed that, we just mentioned that they are uniquely determined by U. And if you just go in the loop of definitions, you will see that this also means that this V that arises is uniquely determined by here. So also in that sense, you can just denote it by gradient U without ambiguity. So so there was no loss of information in the notation. I think this will well, one more thing, a few more things actually. Okay, so nothing great so far. We have two ways of approaching Sobolev spaces: W, weak differentiability, and H, limit of smooth functions. We saw that integration by parts survives, but many more features actually survive. So if you compare to C infinity, what about C infinity is it that you love? First of all, I mean, maybe the only thing is that they have derivatives. Now we don't have derivatives, we have weak derivatives. But there's also continuity properties of C infinity functions. Sobolev functions may not be continuous. They may have poles like this. And by doing some tricks, you can actually have these poles happening on a dense set. So they are notoriously not continuous. But if you take parallel lines to the x-axis, to one of the axes in Rn, on almost every one of these lines, when you restrict your function, it will be absolutely continuous. We saw that weak differentiability characterizes H1P. This property also actually characterizes Sobolev functions. So if you have a function, if you start with an LP function and it has this property, plus the derivatives that you get from this absolute continuity, the one-dimensional derivatives, which means partials, they are also LP, then it follows that the function is in W1P, which is also H1P. So this is also a very strong property. If a function has this, then it is Sobolev. I don't want to get into details of this already. I think burned a lot of time. If you have a connected set and your gradient is 0, this gradient, of course, in the weak sense or in the H1P sense, then it follows that your function is constant. For example, this is still true. By definitions, it's not obvious initially. Some calculus rules still valid, chain and product rules. The kind of part is that actually, for example, if you want to compose U with phi and take derivative, gradient, weak derivative, and do the chain rule, you need stronger assumptions on phi. Both of them cannot be Sobolev, so one of them has to have stronger properties. Trace, so if you have a Sobolev function and you take a nice hyperplane, lower dimensional space, its restriction to here is well defined, but you have to actually be careful with Sobolev functions. And certain Sobolev typos, Sobolev Poincare inequalities are also still valid because you have some sort of inequality, and if you take limit, it remains. I mean, taking limit under integrals usually is very well behaved, so that's why it survives. So we brought in some LP functions to mix with smooth functions, but we see that they still try to be nice and behave like C infinity. But this is only a pessimistic point of view that we're saying, okay, what is still valid? What have we salvaged? What haven't we lost? How about being optimistic and saying, what have we gained? Which is actually a lot. The most important thing we have gained is completeness. The whole reason why we weren't happy with C infinity functions was their limits wasn't there anymore. But with these spaces, H or W, the limits are always there. We have weak compactness, which is very important. Remember in my first example, I said that gradient U to the power 2 is only bounded. We don't know if they are Cauchy. We just know they are bounded. From this actually Poincare inequality, if you bring in, you can also say that this was 2, which is even easier. So you can actually say that this plus gradient ui to the 2 is bounded. Now you only have a bounded sequence in Sobolev norm. Weak compactness guarantees that some subsequence weakly converges. That's a lot. So only boundedness of a sequence implies that you have a convergence in a weak sense, which is enough for many purposes. Another very nice feature of Sobolev functions, which makes them even better than C infinity functions, is that they are closed under some operations like truncation, taking absolute value. These are beautiful properties. So if you've done anything with Sobolev spaces, you will love that. For instance, to prove something, you technically in the proof you need a bounded function. So what do? You have a Sobolev function. You just truncate. You cut it off here, and you replace with the constant. It remains Sobolev. If you want to do with the same with the smooth functions, you have to now, okay, you want to replace it here. You have to, I don't know, patch something nice here. You have to partition of unity, whatnot. Every time you want to prove the smallest change you make to smooth functions, you don't know if they are smooth anymore. So taking absolute value of a smooth functions can do a mess. Imagine you have a dense set of zeros for the function which it switches sign. You take absolute value, you lost even C1 forever. But with Sobolev, you are still in there. That's very beautiful property. And also there's extension property. Suppose you have this domain. A C infinity function can blow up near the boundary to infinity, and there is no hope you can continue it outside the domain, which is here. But actually, Sobolev functions are not as bad. They cannot arbitrarily blow up near the boundary because they have a trace, right? So you see that actually Sobolev functions in some ways are even nicer, even intuitively. So that brings me to the end of a I hope, what is a review of standard unweighted Sobolev theory. And this is a perfect place if you have questions to ask. Anyone? I know you're being recorded. That makes it scary, but. So if not, let's talk about weighted Sobolev functions. As I mentioned, we are not weighting the Sobolev functions, we are weighting Rn. So we have Rn and we put a new measure on it. I want it to be Borel. For example, I want continuous functions to be measurable, right? What less can I want? And often this Borel measure comes from a weight. So the measure of a set is given by integrating a weight against the Lebesgue measure on the set A. Say we define for Borel sets first, and then you can extend it to other measurable sets. So W is never negative. It's locally integrable so that these integrals make sense. Locally Lebesgue integrable. Now that we have two measures, we have to be careful. And dx again stands for Lebesgue measure. So when you integrate this, you get a positive, you get a non-negative number, and this is the new measure mu. So if a measure comes from this weight, we call it weight rather than just a measure. Now again, before what is, we should ask why. So why would we want to do this? What is wrong with Lebesgue measure? It's so beautiful, so why would we give it up? The answer originally comes from 80s, where some people started solving degenerate elliptic PDE. So with the nice PDE, you have a function. You have these matrix of functions, aij, and then partial I partial j of the functions. And for this to be elliptic makes the PDEs very nice, and there's a deep and very extended theory of them. But all of that theory depends on ellipticity of this, whatever it means, I'm not recalling. But then they said, what if you sometimes are not elliptic? What if sometimes you hit zero? And then you can put that zeroness of the weight on the Sobolev function. So you can imagine that your measure, instead of being Lebesgue, has this W dx, and this W contains that zeros of this coefficient matrix. Also, if you have a very irregular domain, you may put a weight which is proportional to distance of the point to the boundary and to some power. And maybe with this weight, you can transform your domain into a nicer domain. And instead of studying something here, you transform it to a nicer domain and study there. The price that you pay is by this weight. So here you will have standard Sobolev space. In here you will have weighted Sobolev, but you can use the results from here to understand the PDE here. And another reason is also from abstract point of view. The theory of metric measure spaces and Sobolev spaces on it is a very flourishing field, has been very, very active since 90s. So these Rn with the standard metric and this measure provide some kind of a test ground for checking theories. If you have something to try on a metric measure setting and see if it works or not, you have conjecture to try, you can come back and test with these things. So if it fails here, then there is no hope. Okay, so how do we define Sobolev spaces on this? The H definition is pretty much just verbatim as before. You define a measure, the difference being that instead of Euclidean, now you have this new measure. And here you have just measure, you don't even have to have a weight.
Hello, Behnam. Just
Yes.
one question here. So here in the case, can you go to the previous slide?
Sure, sure.
So here in this case, this with this weight with this Borel measure mu, is it this H1P coincides with the Newtonian space?
Yes, yes, yes. So,
Okay, oh, I got it.
yeah, exactly. So this H1P will be N1P. So this is the reference is appendix of Bjorn's and Bjorn's book.
Okay,
Nonlinear nonlinear potential analysis on metric spaces, I think. I can show you the book. I have it behind me. So this is where they prove it. It's not easy, but it's very important at the same time.
okay. Thank you.
Yeah, yeah, yeah. Very good question. Thanks. Okay, so as I was saying, you define the Sobolev norm again, except that instead of Lebesgue measure, you have the new Borel measure, and then you can talk about closure or completion of smooth functions under this norm. Technically, you don't take all C infinity, you take those C infinity where the norm is finite to begin with. So first of all, if this is finite for smooth functions, you are in H1P, and then you take completion in that space. We will see more details, of course, about this H very soon. Now, the W definition, which has been like the classical one, you need to have a weight for some reasons. You first require that your function has weak derivative. Now, how do you define weak derivative? Integration by parts, right? U partial k of psi was negative partial k of u, which is just symbolic notation, times psi, okay? But the measure was dx and dx. The weak derivative, even if you have a weight, is still the same. So this is still with Lebesgue measure. And the reasoning is that this integration by parts has close link to Fubini's theorem because you do these partial stuff. And Fubini's theorem is true with Lebesgue measure a priori. So you first require that your function is locally integrable, which was needed just to define weak differentiability. And then you require that it is weakly differentiable, and weak derivatives, again, by definition, are locally integrable. So what was W1P? I mentioned this. So W1P had two components. There was the differentiability part, and then there was integrability part. So differentiability is the same as before. For integrability, instead of looking at LP norm of the function and LP norm of the derivative, you look at the weighted LP norms. So you again look at this up here and say you want it to be finite. So the third component. I mean, these two become the first component and then the second component. This is in some sense unnatural, right? Because you use the weight in a very cheap way, in a very fake artificial way. It plays no role in differentiability itself. So it makes sometimes it ends up working well, but when it doesn't, then this definition is less natural, I believe, than the H definition. But I will have more details on both of these. The reason for the
So,
requirement that I don't want just a Borel measure, I need a weight is for this even to be defined. Because if you are locally Lebesgue integrable, how do you know you are even mu measurable? How do you know mu measurable? Yes, questions are.
so just to make sure, you are defining this weighted W space as a subset of the already defined W space, for which the function and the weak derivatives are in the weighted LP. Is it? Or did I
So
get it wrong?
these are, this W1P is a subset of Lebesgue L1 log. Yeah. So you can say that initially the only space this lives in if you want to go with the Lebesgue measure, is L1 of Rn with the Lebesgue measure. Actually, look, just locally. It's not in LP of Rn. It's not in LP. You can't say it's in LP of Rn.
Okay,
Not
so just
necessarily.
W11 loc, which satisfies this weighted LP integrability.
Yeah. So,
Okay.
so you need these local integrability just to be able to write this equation. That's all. This is the case even in the unweighted case. I mentioned like why, if you are going to say that something is in LP, why do you begin by saying it's L1 loc? Because for your definition to even make sense.
Right, right. Okay, thanks.
Yeah, yeah. So this is yeah, very delicate thing. All you need is L1 locality to even define weak derivatives, but then you don't assume any LP of Lebesgue measure. So I will tell you where these spaces live in. Okay, I will tell you where they live in. Is this the one? No. So it will come after this. Let me give you some pathological examples, right? So far, I didn't say anything, any restriction on the measure or the weight. So you can have some bad functions ending up Sobolev under the H1 definition. It's famously known that Sobolev functions on R1, just R1, are actually continuous. So if you have a characteristic function like this of an interval, this is not even locally in, of course, it's not integrable globally, but even locally, this is not a Sobolev function because it breaks. Okay. Now, if you have a weight that vanishes here, assume weight vanishes near here, it's something like x to 100. It's 100 times vanish. It's really flat there. Then if you chase through the definitions, this can forgive the disconnectedness of f. The disconnectedness of this function u is pardoned by the weight. The weight doesn't care that much about this one point, which sometimes can be a good thing, right? Imagine for some physicists, it's important to actually include this function as a Sobolev function, as a nice function. It shows another way of using weights. You can use a weight to forgive some bad parts for a function. But you can also have more extreme examples. You can even have a function that blows up to infinity like this at one point. But again, the weight vanishes of a higher order than that blow up. And again, it cancels that badness. And it still ends up being a Sobolev function. With the unweighted case, these will have no chance of being Sobolev functions. Similarly, you can have good functions that originally in the unweighted case deserve to be Sobolev, and now they are not. You can have an absolutely continuous function like this. Here, this is Sobolev in the unweighted case, but you can have a weight that is blowing up at one point. Then this punishes this bad behavior here, which is like large. So here, the problem with this function is that the derivative is too large. But it's only at one point, so with the unweighted case, it's excused. But you can put a weight that amplifies it. It says, oh my God, look at this one point. The derivative is extremely bad on a large set. Now 0 is not a small set, it's a big set because the weight around here, if you think about the measure being integral of W around the point. So so it can amplify the small bad parts and make it look horrible. So bad functions can be included, good functions can be excluded. And here's also an example that I will come back later. You can have a function, part 3, you have a function that blows up near the, no, you have a weight that, so imagine this is our n, you have a weight that blows up at origin, and then, yeah, here it's positive. And then you can have a function that is in H1P, which means it's a limit of some smooth functions, but it is not in W1P. Actually, this function is not locally integrable, which means it's also not weakly differentiable. This shouldn't be surprising because for weak differentiability, you're using Lebesgue measure, and for limit of smooth functions, limit is in the weighted measure. So again, it shouldn't be surprising because you use two different things to you use one measure to talk about the limit of smooth functions, and you use Lebesgue measure to talk about differentiability. So there never was any expectation that just being limit of weighted measures should guarantee that you are weakly differentiable. So let's see what we have as conclusion. We see that with H, some bad functions can end up in H. And this last example is showing that W space may not be complete, right? Because it is the limit of smooth functions, but it is not weakly differentiable. So you now again have the problem that you had originally. You have smooth functions, you want to take a limit and you want to stay in the space. So now you have UI here in W1P also because they are smooth, but their limit is not in W1P. So that is one bad thing about W. H, on the other hand, is always a Banach space because by definition, it's the completion of a subspace. Maybe I'll go first and talk about this because I mentioned I want to give you some feeling for where these functions live, right? If you are a limit of in H1P, if you are in H1P, you have smooth functions and they converge to U and their gradients converge to some object V, and they converge in LP, but weighted LP, WDX. So LP WDX. Now WDX is again a complete function. LP with respect to any measure is a complete space. So this would mean that these are smooth. This would mean that this belongs to LP of WDX, LP of the measure. So use UI converge to something, and the gradients of them converge to some vector function, which is in LP of that. So this is basically U, and this is gradient U. Okay. Now I multiple times I mentioned that there's this loss of information in writing gradient of U, and in the unweighted case, because we ended up saying that H is equal to W, and here gradient is unique, from this indirectly we saw that this is actually unique. And this is why, this is where it becomes important. With the weight, this is not guaranteed. That means if you know where these UI converge, it doesn't determine where these gradient UI converge. It's a bit strange in the beginning to wrap your mind around it. How could it happen? Because we always, you give a function, you just write U prime immediately. Function, you write gradient U. But sometimes our notation can trick ourselves. By writing gradient U, you're assuming that if you know U, there is a unique function that you call gradient U. But what if it is not unique, as can happen in this case? So limits of smooth functions are LP functions, and their gradients or the gradients also converge to an LP function. But it turns out that in general, this first component is not determining the second component. So that means this composition map is not injected. This means that you could have one sequence of UI converging to U, and gradient UI converges to V1. Now you could have a WI sequence converging again to U, but gradient WI converges to V2, which is not the same as V1. It's sometimes said if you read a paper or something, they may say the same function has two gradients. The problems, part of the confusion comes from the same. What same? As functions here, this u, which comes from limit of wi and gradient wi, is not the same object as the one coming from vi gradient vi. So these are not same. They are different objects in H1P space, but their projection onto LP happens to be the same. It's like XY axis, you have 2 points like this. Because their projection here is the same, it doesn't mean these two are the same points. But we are so used to the unweighted case in which, if you think about it, Sobolev space sits like this. So the projection uniquely determines the functions. So these are gradients, these are the original functions. So in the unweighted case, these projections are injective, but with weighted, it becomes like this. So sometimes the projection is the same function, but these are different objects in the space. So this would be a mess, right? Imagine like you can't even write gradient of a u. That would be a very scary Sobolev theory. Sobolev theory is already crazy, and let alone having these. But fortunately, SEMS, and these are 97.8 results, he proved that if you have a p-admissible weight, then this never happens. So gradients are always unique. So if you have any questions, let me know, and I'll go back and explain these words here. So a consequence here is that this H1P sits in LP, but with the measure, with the new measure, not so. And W1P similarly, W1P also sits in LP, but with respect to the mu. The difference between H1P and W1P is that W1P is also required to be in L1 log of not weighted. And that's just the technical requirement so that we can define weak differentiability. So this is a W1P, but H1P may not even be L1 log, which we saw in this counter example that I had. You had, yeah, here. So you have this U function. This is not locally integrable, but it is still in H1P. And that because it's not locally integrable, it's not in W1P. So both of these spaces are subsets of LP of the mu measure. And they come from different places. So H is limit of C infinity and W is this. So we saw that in general, things can go bad. Bad functions can be in, good functions can be excluded. So we have to look at some nicer measures. And those nicer measures are, first of all, you need the doubling. You need that the measure of ball with twice the radius is not hugely more than the measure of the smaller one. So the growth in the measure by doubling the radius is controlled by a universal constant. The doubler measures has a big history and they have very nice features. One of them is that the Lebesgue differentiation theorem still holds, that for almost every point, the average value of a function over a ball converge. If you take smaller and smaller balls, the average converges to just the value in the center almost everywhere. And another thing that we require of weights is that they satisfy this P-Poincare inequality. This ends up being really kind of crucial. It has been singled out as the one feature that makes everything so much nicer, including with weights. So you have a ball, and then you have a function that is smooth on the ball, and you want it to be bounded to avoid this blow up near the boundary issue. And then you look at average of the function on the ball. All makes sense, continuous, nice functions. And then you subtract the average from the function and you integrate again the absolute value. And you want this to be controlled by average integral of the gradient to the power p on the ball. So it's just a quantitative control on how much the function can oscillate from average in terms of the gradient. You can see that if the gradient is 0, you must have 0 on this side. That means the function should be constant. So it's a control over a function by its gradient. With Lebesgue measure, this is true, but with a weight, it's not guaranteed. So it's a definition. So maybe it wasn't clear. So this is a definition. I will add this in the slides when I share. And for short, we say that a weight is P admissible if it is doubling in the previous sense and it has this P punker. So these are P admissible weights. The theory becomes much nicer with these. So are there P admissible weights? Well, many of them. Lebesgue measure is one. And if you are away from the Lebesgue measure, remember, if W is just 1, then you just get standard Euclidean space. So if you are away from this 1 by only a control amount, you're away from 0, away from infinity, your weight doesn't become 0, doesn't blow up, then you are still very much close to being Lebesgue and you have P admissible. Another very famous class, I won't recall their definition, is Mackenhout AP weights. Classically, these theories have been developed only for these. Powers of Jacobians of quasi-conformal mapping. So if you have a quasi-conformal map from Rn to Rn, you compute its Jacobian, and 1 minus P over N, I believe. This becomes P admissible. If you have a superharmonic function on Rn, it is a P admissible weight. And finally, if there are some theorems saying that if you have some set F and you look at a weight which is distance to this set to some alpha power, alpha sometimes can be even negative, then you have a P admissible. So there are a large class of weights which are P admissible. So what happens with P admissible weights? The first thing that I already mentioned is that, first of all, gradient is unique for in both senses, which is great. But many other features also are true. H is always a Banach space. This didn't need any P admissibility. It's just completion, so it's there. Smooth and Lipschitz functions become dense in H. So these are nice properties. Some of them are true without P admissibility. Some may need P admissibility. So I didn't want to get into technicalities. Weak compactness, which I mentioned, just from having a bounded sequence, you want to derive convergent sequences. Calculus rules hold. This lattice property, again, holds. If you truncate a Sobolev function, cut it off, it remains Sobolev. Poincare Sobolev inequalities with this weighted version still hold. So if you want to read a lot on these, the book by Heinonen, Koskela, and Martio. Oh, wait, not Koskela, sorry. Kilpilainen. So they have a beautiful book on nonlinear potential analysis, which is just these H space, and it's beautifully written. All the lemmas are proven. So there are proofs of all of these stuff. Okay. H or W. Is H equal to W, right? Remember, one of the best results in the unweighted case was this, and because then you can prove a lot of stuff for Sobolev functions. Sometimes you use this H definition to prove something. Sometimes you use W definition to prove something, and when you know they are equal, then your hand is open, right? But in general, no, even with P admissible weights, they are not equal. The example that I had just shown you with this ux x to the minus n plus 1, the weight there was actually P admissible. So this was x to some gamma, gamma bigger than n, P minus 1. So this was in W, but not in H, although the weight is P admissible. We had seen in the example that some functions in H may not be locally integrable, so therefore they are not even weakly differentiable. Again, it shows that H is not inside W. This also shows W is not inside H. They are different spaces. And one condition that guarantees weak differentiability of H1P is that this power of weight becomes locally integrable. This comes from Hölder's inequality. It's nothing really to be memorized. So it's just the right condition so that this sits in H11 of our n, not weighted. If this is true by Hölder inequality, you easily prove that this is there. But then functions here, this is unweighted classical Sobolev, and these are weakly differentiable. So that's why. And if you have Mach and Haupt AP weights, these are equal. This is one of the reasons why originally they only did with AP weights. So they become equal. And my final slide, with W, if single point may not be removable, maybe next time I will next time talk about just removability. One of the nice things about Sobolev functions over smooth functions again is that if you have a very small set and you know your function is Sobolev on the complement, it is actually Sobolev on the whole thing. With C infinity, that's not the case because you have to check at every single point. A function can be smooth everywhere except the origin, but well, at the origin it can fail, like absolute value of x, but not with Sobolev. And so this is a bad point for W. The bad point for H was that it may not be weakly differentiable, but then that means the gradient of U is just this abstract notion that some UI converges to U and their gradient converges to this. There is no other meaning attached to this. So is it really a derivative? We don't know. So that's bad point for H. On the other hand, H is complete. W may not be complete. So maybe 2 negatives for W, 1 negative for H. Maybe H is a better space. I don't know. But the best is when they are equal, right? But they sometimes are not. Thank you so much, everyone, for your attention. I hope I didn't go over time. That's one of my nightmares.
I am audible. Yeah. So thank you, Behnam. Do we have any questions? Okay, so I have some few questions regarding this. Can you go back to the previous slides?
Let me know when.
So suppose, yeah, with this one only. So if we have a P admissible weight and we want to construct a new weight, let us suppose, let us say we have a P admissible weight W, and we are constructing a new weight such that a new weight mu, so that d mu equals to W dx. Dx is where dx is a Lebesgue measure. So whether this kind of transformation again going to give us P admissible weights?
Okay, so I couldn't quite understand the question. So you already have weight or you don't? So let's forget so measures. So you have d mu W dx already, right?
Yeah, and here W is already a P admissible.
Yes, so this is P admissible.
So this mu.
Yeah, so W is just mu. Like I mean, in language we identify them. So when I say W, when I say W is P admissible, it means mu is P admissible and vice
Okay.
versa. So some books actually just write, for example, W of A, measure of a set, to mean measure of A. So instead of having two notations, yeah. I originally when working on this research that I had, I was trying to remain flexible and work with measures whenever possible. But effectively, you end up needing that the measure is absolutely continuous with respect to Lebesgue measure. And when you're absolutely continuous, then Radon-Nikodin says that this is actually just a weight.
Yes.
So it's a question of is your measure absolutely continuous with respect to Lebesgue measure?
Lebesgue.
Yeah.
So like,
Do you want an open question on this problem? It's quite well known open problem. It's in the same book by Bjorn. Suppose you have just measure, and you know that this is P admissible.
Okay.
It is doubling and it has Poincare, which are well defined with any measure. So the open question is, does it imply that actually mu is a weight? If you have a P admissible measure, is it a P admissible weight? I believe it's still open. Some people claim to have the answer, but it's a very nice question.
So it is about like asking whether mu is absolutely continuous with respect to the Lebesgue measure.
Yeah.
Oh.
For H1P, you don't need absolute continuity. You can just define the same set of functions as a limit of C infinity. For W1P, you need absolute continuity for a very artificial and stupid reason. You want to define weak derivative, you need local integrability with respect to the. And then the question becomes, if you are mu measurable, if you are ln measurable, are you mu measurable? And that effectively forces you to assume absolute continuity.
Okay.
Hello.
Okay.
Hello, sir.
Yes.
Can you hear me?
Yes, sure.
Yeah. So I have one doubt that I wanted to ask that. So there is a notion of weighted, like here you are taking W as a weight, right?
Yes.
So is there any notion of like if we take metric?
Oh, so you want to play with the metric, not the measure of Rn.
Yeah. So if we replace that gradient portion, by just a matrix, let's say A is a matrix, so Ax times grad Ux, inner product with grad Ux, that weight you are imposing on the that gradient part. So in that case,
let me write it. So you're saying that.
Suppose
Are
you
you talking
define the
about?
norm.
Wait a second. This norm?
Yeah, you just keep the LP norm as in this norm. So in terms of gradient part, you just write it as that integral of A times A is a matrix. A grad U inner product with grad U.
Oh, okay, like this?
No. A grad U, then
okay.
it is a matrix multiplication. Then you just take
okay.
an inner product.
AX, UX, and then you do UX.
No, you take grad U.
Grad. So grad and then grad.
Grad, right.
Yeah. And then you integrate
it over with respect to Lebesgue measure. Yeah.
Okay, Lebesgue measure.
So this is a matrix weight, right?
Yep.
Yeah. So do you know any similar kind of result for this kind of weight, that whether this H1 here P equal to 2, H12 is W12, both are equal or not? Or what are the necessary and sufficient condition on A so that these two spaces are equal.
So isn't this just if you are doing P equal 2, so this is gradient U to the 2, and
If you
then
take A is
absolute gravity.
identity,
Okay, A is not, so you cannot separate A here, right?
right?
I'm sure this has been looked at, but I don't recall any single reference to give you, but definitely this.
Okay.
So when I mentioned the motivation for studying, these weighted spaces, I mentioned this these degenerate PDEs. Actually, that could be exactly there, this AX.
Yeah.
So I think what happens is you pull out the degeneracy part, and then you end up with some other matrix BX times that. Now this becomes elliptic, and this contains all the degeneracy in it.
Okay.
Yeah, one way to get from that to this is at least going through this. So if you can factor out basically the degenerate parts, any part where AX blows up or becomes 0, if you can put them inside the WX, then the remaining part may be elliptic.
Yeah, this can be done.
But I would look at the book I mentioned because both of them actually, because once they build this theory, they start doing all these nonlinear potential analysis with this kind of PDE questions. I'm not really a PDE person. I'm lying to everyone here. So I don't know any Sobolev theory, Sobolev spaces. I do analysis on metric spaces, and that's the path that I have taken to end up here.
Okay.
Do we have any other question? Okay, so if not, let us thank our speaker. Thank you, Behnam.
Thank you, everyone. Let me see.
So we'll meet in the next session.